the session about the GNU Compiler Collection, or GCC for short. In this session, we are going to talk about the compilation flow and answer the question how the source code is converted into a binary that can be executed on a CPU. The compilation flow consists of several stages, such as the preprocessor, debugger, the actual compiler, and assembler, to name a few. Since this course targets embedded systems, the flow ends with the upload of the binary into the microcontroller unit, or MCU for short. What will you need this session for? Later in the course, we are going to talk about assembler and write assembly code. If you would like to study how the GCC converts your source code into assembly, you will know how and where to interrupt the compilation flow. Or you have multiple source files and would like to combine them into a single binary. Where and when does this happen? Further, the session will cover the major compilation steps so you become aware how to fix the compilation of your code in case of errors. Throughout this session, I'm going to use a simple demo program, Hello World. It does not do anything specifically, but just prints out Hello World on the terminal. Are you ready? Let's get started. Here are the major steps that your source code passes through on its way to become an executable binary. Usually, the entire compiler chain is invoked by executing the GCC command. In our case, we compile helloworld.c by typing in GCC, followed by the source code file helloworld.c, and specifying the output file hello world using the O parameter. Every stage that you see here has its own dedicated purpose, which we will be discussing next. The first stage of the journey of your source code through the compiler chain is the preprocessor. It processes all directives which start with a hash. For instance, here in this example, the developer indicated that the literals max should be replaced by 5. Then, the preprocessor scans through the source code and replaces all max with 5. Hence, hash define is quite different from, for instance, const int max equal to 5. The former is not even seen by the compiler, which is at a later stage, since max has been replaced already in this step. In the case of a constant integer, the compiler reserves memory space and marks it read-only in worst case. In many cases, the compiler will also replace max by 5, but we cannot say for certain. Hence, as a memory-saving measurement, avoid using constants in your source code and define them using hash define. We already talked about hash define, but what else does the preprocessor do? Another functionality is to replace the hash include directive. The preprocessor copies the entire content of the referenced file, here it is stdio, replacing the hash include directive while doing so. Hence, after the first iteration and inclusion of stdio, our Hello World program looks like this on the right. As you can see, it again includes directives. The preprocessor keeps executing the directives in several iteration steps till all of them have been processed, and our Hello World program will look like this. If you would like to see it for yourself, invoke the GCC with the -E option as shown at the bottom of the slide. In the next session, we are going to talk about the next stage, the debugger. The debugger essentially checks if the source code contains any syntax errors. For instance, our Hello World program is missing a semicolon in line 4, right here. When the source code is then compiled, the debugger throws out an error message stating what exactly went wrong, namely in line 4 and column 26. Keep in mind that the debugger sees the code from the preprocessor. Hence, if there is an error in any of the directives, the error message might be a bit confusing. Imagine the developer wrote max 5 and accidentally added a semicolon at the end of 5. Hence, the preprocessor replaced all occurrences of max with 5 and a semicolon, and hence the source code that the debugger sees will look like this. Obviously, this is not correct. In this case, the debugger is quite smart and points out the correct error. However, if you get a cryptic error message about a part of the code that is not in the line the debugger complains about, it is always a good idea to check for macros and directives inserted by the preprocessor. In the next step, we will finally talk about the compilation stage of the compiler collection. This is what most developers refer to when they talk about the GCC. The compiler takes the source code modified by the preprocessor and debugger and converts it into instructions, registers, and names memory addresses. Hence, after this stage, the source code becomes architecture dependent, since the compiler knows what the hardware constraints are. That is, the compiler is aware how many registers are there in the CPU, how many memory addresses, and what instructions the CPU supports. When the GCC is invoked with the flag S, the compiler chain will output the program converted into the so-called assembly language only. It contains mnemonics representing the instructions. Some of the mnemonics are here in blue, such as push Q and move Q, shown here and here. To understand the meaning of those mnemonics, one has to consult the reference manual for this particular processor. Different processors support different mnemonics and therefore different instructions. For instance, the MCU Atmega 328P has support for 131 instructions in total, represented by 131 mnemonics. A look into the reference manual reveals all of them, including a description, their functionality, and the side effects, such as the setting of flags and the number of clock cycles required to execute this particular instruction. For instance, the mnemonic adds two registers RD and RR and stores the sum into the destination register RD. To do so, it requires one clock cycle and might set the flag Z, C, N, V, and H. Later, more about the flags, what their purposes are, and what they can be used for to optimize a program. Great! This was a short overview about the compiler. In this session, we will talk about what happens to our Hello World program at the assembly stage of the GNU compiler collection. The assembler takes the code from the compiler and creates object code. To interrupt the compilation flow after the assembler, invoke GCC with the C flag. The output of the assembler is in the so-called executable and linkable format, or in short ELF. It is a standard defining how binaries look like, and it consists of several sections, with each section having a unique purpose. Every ELF binary starts with the ELF header, which, among others, contains information regarding the architecture, operating system it is supposed to run in, data format, and file version. The ELF also describes sections for different types of data. Here, we have to distinguish between uninitialized and initialized data, and furthermore, between data with different access rights. Variables are read and writable, and hence are placed in the section Data, while constants are read-only, and therefore in the section RO Data. Any uninitialized variables are placed in the BSS section. Not less important is the text section, which contains the instructions of our program. Let's dig a bit deeper and have a look at the ELF file of our Hello World project. Here is an example for the ELF header. The header can be displayed using the command read ELF with a H flag. As you can see, it starts with a magic that indicates that this examined file is indeed in ELF. It also contains the architecture the Hello World program has been compiled for, here in line 10. It is a 64-bit Intel compatible architecture together with the operating system in line 7 and several other information, such as an indication that the data is in 2's complement and little endian format. To list sections available in the ELF file, invoke read ELF with the S flag. As you can see, the Hello World program consists of 13 sections. The first 5 are text, relay text, data, BSS, and RO data. So far, we have not discussed the purpose of the section relay text. It contains relocation information for the text section. This relocation information can be data that is not yet included in our program. For instance, at this stage, we cannot execute our Hello World program because we do not know anything about the function printf. Let's have a look at an example. We would like to know the content of the RO data section. Going back to the assembler code, we see that the compiler decided to store the string hello world into the RO data section with the first character of the string at ages LC0. The string itself is data which is not modified. The compiler recognized this optimization and therefore marked the string to be read-only. Let's confirm our hypothesis and extract the content of that particular section by invoking readelf with the X flag followed by the desired section name. As you can see, our hypothesis is correct. You can even see the ASCII character for capital H, that is right here, followed by lowercase e and 2 L's, and so on. Also, the string ends with a null character, whose value is 00 in hexadecimal format. Great! This was a brief overview about the assembler. In the next session, we are going to talk about the linker, the last step of the compilation flow. Essentially, the linker will take the object code and create an executable file of our Hello World example. As mentioned earlier, currently the object code has just a reference to the printf function, but so far we do not know where the function is located nor how it looks like. The linker replaces these placeholders with references that point to the correct function. However, often in embedded systems, the functionality needs to be directly integrated into the executable as there is no file system and hence no libraries available in those systems. In this case, the functionality is copied directly into the executable instead of just referencing it. This is called a static compilation or static linking, and in our case, the code of the printf function would be directly integrated into the ELF file, increasing its file size compared to the Hello World binary linked dynamically. To show the libraries a binary depends on, the tool LDD can be used. The dynamic compilation created an executable which depends on libc among other libraries, while for the static compilation, the binary does not depend on any library. This independence is paid for by a much larger file size of more than 740 kilobyte compared to 16 kilobyte the dynamic executable occupies. This is the end of the compilation flow. However, since this course is about embedded systems, we added 2 additional steps to the flow: the object copy and the uploading. Especially in an embedded system environment, the executable file might need to be converted into the so-called Intel hex file format. That is achieved by invoking the tool object copy with the parameter capital O, indicating the format of the output file. This example shows the Hello World program is converted into the hex file format. In this format, every line starts with a colon, followed by 1 byte indicating how much data the current line contains. This is marked in red here. The next field of 2 bytes in green specifies the address where the data of the line is to be copied to in our program memory. The address field is followed by the record type of the data. Among others, 2 record types are important. 00 indicates just plain data, while 01 stands for the end of the file. The field that follows represents the actual data of 16 bytes as indicated in the red byte count field, followed by the checksum in gray at the end of the line. If all bytes of the entire line are added, the least significant byte of the sum needs to be equal to 0 to indicate that no error occurred. And that brings us to the last session of the compilation flow, the uploading. We are going to talk about the upload mechanism to execute our Hello World program on the microcontroller unit, or MCU for short. Since in this course we target Arduinos, the session is specific for this platform. However, the upload stage is representative for uploaders for other targets. Hence, if your embedded system differs, please refer to the documentation released by the manufacturer of your platform. For Arduinos, the programmer first issues a reset to load the bootloader. Within 2 seconds, the bootloader expects data in Intel hex format, discussed earlier. While receiving the data, the bootloader copies it to the indicated memory addresses in the program memory. Optionally, the programmer rereads the program from the memory to ensure that no error occurred, following by a reset. Therefore, again the bootloader waits for 2 seconds. However, the programmer exited in the meantime and no new data is sent. Hence, after the 2 seconds expire, the bootloader surrenders its control to the newly uploaded program, which starts to execute on the MCU. Since we target the Arduino platform in this course, for uploading we will use avr-dude. In this example you can see that the hello world.hex is uploaded. First, the signature is verified. This ensures that we target the right architecture. The signature is a string of data that is burned into the chip. In case of Arduino, which has an Atmega 328P MCU, the expected signature is 1E950F. After the signature is verified, the program is copied into the memory, followed by a verification of the data written. Then avr-dude issues another reset and exits, while the MCU reloads the bootloader and the freshly uploaded program. This is the last step, and hence it completes the compilation process. So what did we do in this session? In the session, we covered a brief overview about the compilation process and the purpose of the individual stages. Further, now you are aware how the flow can be interrupted, allowing you to examine what the previous stage achieved. Further, we extended the compilation flow by adding the transformation of the ELF file into a hex file and the uploading mechanism. Don't worry if some of the aspects are not clear. Later in the lectures, you can always come back here and have a look at it again. And that brings us to what is next. In the next session, we will review a bit of the C language, the de facto standard for embedded systems. Since in C the developer is responsible for the memory management, we will have a look at pointers from the embedded system's point of view. Don't worry, it is not as complicated as it is explained in the lectures you had in your past. Further, we discuss mistakes that happen quite easily and often, and what the consequences are in terms of security and stability, and how to fix them. Stay tuned and see you in the next chapter. Thanks for watching.